Hello everybody, welcome back. In this tutorial, we're going to be covering quiz number 29, which introduces the concept of virtual work. As you guys will see, quiz number 30 also extends these concepts of virtual work. However, quiz 29, we're just kind of dealing with the basics. Now, virtual work is going to be a really interesting topic. I don't really know what to say about it because to me personally, it's a very complex topic. Now, what makes it even harder is virtual work has a lot of shortcuts, if you will. If you guys know virtual work really well, like Dr. Sammer, he can make problems look extremely easy. The problem with this is once you compare someone's solutions, if they know it very well, to the theory, it doesn't really line up very well. So, what I'm going to do is I'm going to try and keep it all to the theory. So Dr. Sammer's online notes, which he generously provides, I'm going to use those as my only point of reference. I'm going to skip all the shortcuts in virtual work so I can show you guys, all right, if you have these theoretical equations, this is how you apply them. Now, Dr. Sammer, he likes the shortcuts, and I don't blame him. Shortcuts are always nice. However, it makes trying to understand these questions really difficult. So I'm going to try my best to show you guys how to solve these questions straight from the theory. All right, so with that being said, let's jump into that theory. So in this quiz, we're going to be focusing on the virtual work in reference to beams. So as you guys know, the last couple of weeks, that's what we've been talking about. Beams, 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 and yes, now we got more beams. However, the principle of virtual work, it's really simple. So it's based on static equilibrium, and the essence of it is this. The internal virtual work, often termed as IVW, is going to be equal to the external virtual work, EVW. All right, so we have one equation is going to equal another equation, so therefore we can solve for an unknown. As you guys are going to see next quiz, there's many applications in which unknowns we can solve for, stuff like that. But now we're just going to talk about, all right, if we apply these two equations to beams, what do we get? So the first scenario that we have is those flexural beams. So these are the ones when we load a beam either with a distributed load or a point load, and we're interested in how much it deflects downwards or upwards, something like that. Well, we get the following equation. So the internal virtual work for this will be the integral from a to b. Dr. Sammer has it from 0 to L, but as you guys are going to see, there may be many sections. So what I like to do is I like to go the integral from a to b of EI, which is that flexural rigidity, multiplied by the second derivative of our deflection function, also multiplied by the second derivative of our virtual deflection function. We're going to talk about that a little bit later, and this will all be with respect to dx1. Now again, that's going to be the internal virtual work, and we're saying that this is going to be equal to the external virtual work. So the external virtual work, even though it looks a little bit complicated, it's the integral from a to b of q multiplied by our virtual displacement function with respect to dx1. So that in essence is capturing the effects of the distributed load minus the shear at B multiplied by the virtual deflection function at point B plus the shear at A multiplied by the virtual deflection at A plus the moment at B multiplied by the rotation at B minus the moment at A multiplied by the virtual rotation at A. So this is how you guys will see it in the exact notes, and this is where things get confusing. Because even though you see this in the theory notes, whenever you go to somebody's example of virtual work, they apply it a lot differently. And very rarely do you see the V terms or the M terms or anything like that. So I'm going to show you guys exactly what these means when we get into the examples, all right? So this is the bit more complex equation, but we remember that there was actually two types of beams we talked about. So we talked about flexural beams, but then we also talked about axially loaded beams. So these are the beams that they're just sitting there in space and I take one end of the beam and I start pulling it laterally. So you guys have seen that a lot. It shouldn't be too new to you guys. And the internal virtual work for these beams is going to be the integral from A to B multiplied by EA, so that's the axial stiffness, multiplied by the first derivative of that displacement function, multiplied by the first derivative of that virtual displacement function, all with respect to dx1. So that's going to be no problem at all. On the external work side, we have the integral from a to b of p multiplied by our virtual displacement function times dx1, or I guess with respect to dx1. So p in this case, that lowercase p, that's the same thing as a distributed load, except in this case, instead of going downwards like q, this one's going laterally. So that's why we term it p rather than q, so we don't get those two mixed up. Now, just like before, above where we have all the V and M terms, well, down here we have EA multiplied by the first derivative of our displacement function, multiplied by our virtual displacement at point B, minus EA multiplied by the first derivative of our displacement function multiplied by the virtual displacement at A. Now, all this is a real mouthful and really kind of difficult to understand if you guys ask me. This is why I don't like virtual work. It's very hard to understand, but once you guys get it, you guys will get it very well and it's going to be no problem at all. So just kind of keep this at the back of your mind. Don't think about it too much. We're going to go into the examples now and hopefully this can make a little bit more sense. All right, guys, sound good? Let's jump into the examples. Alrighty guys, welcome to the quiz. As you guys will see, this quiz isn't too bad. It's only 3 questions. However, it might take a while because not only are we going to solve the questions, I'm going to do my best to explain what's going on in these questions so you guys can really understand what we are doing when we talk about virtual work. Because again, that's what I think the main problem with virtual work is. It's simple to understand once you understand it, but it's a real bitch to try and initially understand. All right, so let's go through them one by one. As you're going to see, we're going to cover both a flexural beam as well as an axial loaded beam. So by the end of this, you guys should be experts, or at least that's what I'm hoping for. All right, so if we look at question number 1, it says the shown beam has a constant cross-sectional area A and a length L. The beam is under the effect of an axial end force P and an axial distributed load small p of force per unit length. When applied to the beam, the equations of the principle of virtual work would have the following form. So if I scroll down here slowly, as we can see, we're given 3 options, option A, option B, and option C. And then we're given a 4th option, option D, which basically says that option A, B, and C, they're all the same. They all represent the principle of virtual work for this beam. All right, so let's derive these equations and see which one of these is the correct answer. Now, if we look at the beam above, it's a fairly simple beam. It's an axially loaded beam, so we're pulling with that orange force P. And then we also have a distributed load, small p. So if we come down here, I wrote exactly what we had from the theory right here. For an axially loaded beam, we have 2 factors. The first one over here on the left-hand side, which I'll underline over here, this is what we said was the internal virtual work. So I'm going to go not W, not yet anyway, IVW. So this is the internal work of an axially loaded beam. And we had a second term, which I'll switch over to blue here. And we said that this term right here, this was the external virtual work. So what I'm going to do is I'm going to go external virtual work. And again, this form right here, this is the form you would see it in a theory, in a textbook, something like that. So what we're going to do is we're going to take what we know from the theory and apply it to our very specific case. All right, so what we're going to do is we're just going to take it one step at a time. And the first thing we're going to discuss is that internal virtual work. So I'm going to go IVW, and we say, all right, well, the first thing that we're doing is we're taking an integral. Now, if we look at the theory, we say it's from A to B. What this means is we're taking the integral over a region that is smooth and continuous. All right, Clayton, that doesn't sound too bad. So if we look up at the picture here, and we know that at this end, we have x1 is equal to 0, and at the other end, we have x1 is equal to L. Now, the question becomes is, when does something become discontinuous, or when does something become non-smooth? Well, that happens if there's a concentrated axial load or moment. Now, if we look at this, between x1 is equal to 0 and x1 is equal to L, there is no concentrated load. We do have a concentrated load P, but that's at the end, so we don't have to worry about that. So going from x1 is equal to 0 all the way to x1 is equal to L, it's valid because it's going to be a nice smooth function all the way across. So now that I know that it's nice and smooth, I can come down here and say, all right, well, instead of my integral going from A to B, I know it is smooth all the way from 0 all the way to L. So I can go, all right, I'm taking the integral from 0 to L, and we know that EA, well, that's just going to be EA. And then what we're doing is we're taking the derivative of our deflection function or our displacement function. So I'm going to go du, and more specifically, since we're looking at the case in the x1 direction, I can go du1, and this is of course going to be with respect to dx1. And then the next one is the derivative of our virtual displacement, so I'm going to go du1 star, and again the star is meaning it's that virtual displacement, but this will also be with respect to x1. And then we have dx1. So as we can see, the internal virtual work after we apply it, looks fairly similar to the internal virtual work from the theory, and that's expected. So that's not going to be a big deal for us. Where things are going to change is when we start talking about the external. And is this the same blue? I can't tell. I think this is a little bit darker. So what I'm going to do is I'm going to swap it so it doesn't look so bad. All right, so now we're going to talk about the external virtual work. And this is the one where it starts getting a little bit confusing from the theory equations. All right. All right, so if we look at this, again, everything's in terms of A and B. But now if we look up at our function, we defined what A and B are. So at the very left-hand side, this is point A, and at the very right-hand side, this is going to be point B. All right, so now that we know that, we can come down here and we say, all right, well, the first thing that we're interested in, and I'll highlight it here, is the integral of our distributed lateral load P. Now, if we remember from the question, we actually do have this lateral distributed load. So we're going to be taking the integral. And instead of A to B, we know we're going from 0 to L of P multiplied by our virtual displacement function U1 star with respect to dx1. All right, so that's what I have highlighted. Again, we have that distributed load, so we have to include it. All right, so I'm going to erase this now, and then we're going to look at the next term. So the next term right here is plus EA multiplied by the first derivative of our deflection function multiplied by the virtual displacement at B. So this is going to be the key here. I'm going to erase the highlighting and I'm going to circle this right here at B. So if we look up at the top here, what I'm interested in is I'm not interested in the whole displacement field as a whole. I'm just interested in the displacement at location B. Now we know from the picture here that displacement will be non-zero. Once I pull with that force P, of course that point B is going to move a little bit to the right. So what I'm going to do is I'm going to come down here and say, all right, since we know that we have that, I can include this term. So I'm going to go plus EA multiplied by the first derivative of that displacement function. So that's going to be du1 with respect to dx1. And then multiplied by u star at B. Now, what do we know about u star at B? Well, we can find u star B because it's actually the same as our virtual displacement when x is equal to L. So I can put x1 is equal to L, just like that. Because again, if I'm looking at the top here, u star at B, that's basically measuring this point right here. And I can find how that point travels since I have that virtual displacement u star. I just have to substitute the value x1 is equal to L. All right, so that's not too bad. Let's come down here and look at the last term. So I'm going to erase the highlighting yet again. And we're going to take a little peek at that last term, which is this right here. So again, it's the exact same where we have EA multiplied by the first derivative of our displacement function. And then we multiply it by the virtual displacement at A. So if I scroll up at the top here and say, all right, well, point A, that's over here at the fixed end, over right here. So I'm putting a nice blue circle. And I realize that that point does not change. There is no virtual displacement because we have fixed that point. Therefore, since this is fixed, we know that u star at A is equal to 0 because we have that boundary condition. So when I come down here and I look at my external virtual work, and I'll try and keep it on the screen here, I do not include that term because I can include it, but if I go u star of A, well, that's equal to 0, so we basically have nothing conclusive right there. All right, so now we have our two equations, and then the key to virtual work, I'm going to scroll down, is we always say that our internal virtual work, so I, V, W, is equal to our external virtual work. So what we're going to do is we're going to set these two as equivalent to each other. So if we're looking up at the internal virtual work, we see that we have EA. Now the question says that those are constant values, so therefore we can take them out of the integral. So I'm going to multiplied by A, and then I'm going to take the integral from 0 to L multiplied by the first derivative of our displacement function. So I'm going to go du1 with respect to dx1. And then we multiply this by the first derivative of our virtual displacement function. So du1 star, and of course this will be with respect to dx1 again. And then we have a dx1. Now I'm probably getting a little bit crooked as I write that. I apologize. And again, this is the internal virtual work. Now what we're going to do is we're going to set that equal to the external virtual work. So looking at the first component there, we have the integral again from 0 all the way to L of small p multiplied by our virtual displacement function u1 star with respect to dx1. And then we have our second term, which is EA multiplied by the first derivative of our displacement function multiplied by u star 1. Now, before we do that, what we're going to do is we're going to take a look at this term right here. So right here we have EA multiplied by the first derivative of our displacement function. Well, we know that this is actually equal to EA multiplied, and remember, the first derivative of the displacement function is actually the strain function. So this is the same as saying E11. All right, so we can actually go a bit further because we also know that EA multiplied by the strain, that's the same as that axial load P. So that's the big P right there. This is the one in orange. So if I substitute that in, I get actually in my equation plus P times my virtual displacement function 1 at the value of x1 is equal to L. So x1 equal to L, just like this. So now that we have this equation here, we can go up and say, all right, hold on one second. This is one of the options. So if we look what we just written down, and let's try and change colors so we can really highlight this. This is the exact same as option C. So this is going to be a problem though, guys, because just because one of them works doesn't mean it's just that one. We have to check the other ones. And as you guys are going to see, the other ones are going to work just fine. All right. So this is what we have right now. And actually, I'll scroll down just a little bit more. And then this is option C. So right down here, I'm going to put that this is option C. Now we can manipulate this a bit. I'll change colors because we know the relationship du with respect to dx1. This is actually equal to the strain. And we did that above up here. So remember up here, we took this du with respect to x1, and we said that that is actually equal to the strain. And we did that in the external virtual work. But however, we can also use that relationship in the internal virtual work, because as we can see, we have two parameters right there that are du's with respect to dx1. So as we know, if we look up really quick, all of the final answers over here, they all have the exact same. So we're not going to worry about trying to manipulate the external virtual work. We're just going to look at manipulating the internal virtual work for now. So I'm just going to put this is always equal to blah, 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 because this right here, we're not going to modify this right now. So all of this right here, I'm just going to say is the external virtual work. All right, so let's substitute what we have in. So we can say, all right, well, now we know that we have the integral from 0 to L, and I'm going to put EA inside this time. du1 with respect to dx1, well, we know that that is simply the strain 1, 1. du1 star with respect to x1, well, we know that this is actually the strain, virtual displacement strain. All right, and then we can go, of course, this is all respect to dx1, and this is equal to the external virtual work. So if I take what we have right now and we look up at above, well, it doesn't quite match A or B, so we haven't really done anything yet. So the next thing that we're going to do is we're going to say, okay, what about this area term? So we have an area term right here. Well, since A is constant, we know that the area is actually going to be equal to the integral over dA. All right, so what we can do is we can substitute that bad boy into the equation. What we get is we get the integral from 0 all the way to L, and then we have a second integral here of E times epsilon 1, 1 times epsilon star 1, 1 multiplied by dA multiplied by dx1. And of course, this is equal to the external virtual work. So if we look up at the top here, we can see that this one actually matches part B exactly. So we can say, all right, well, now we also know that part B is correct. So by this point, we could conclude that it will be D, all of the above. But our last question, of course, is, well, how is A correct? So we know that A is going to be correct, but how do we get A? Well, as we're going to see, it's going to be nice and easy because we're just going to utilize one more nice relationship. and that is this one right here. So we know that E times epsilon for a linear elastic material, so a linear elastic material, this is actually equal to sigma. So therefore I can substitute that bad boy into the equation. I get that we have the integral from 0 to L multiplied by the integral of sigma 1 times the virtual strain epsilon 1 star times dA times dx1 is equal to the external virtual work. All right, guys, so that's going to be question number 1. It shouldn't be too bad of a question as long as you guys know the relationship for actually loaded beams. So what I recommend for you guys, if you guys are going into an exam type scenario, just remember this equation for actually loaded beams, and then you can apply it to whatever beam you're given in the question. It'll just be a matter of substituting things in. And if you guys want, we have a bunch of relationships, as you guys have seen down here, in which we can substitute things and rearrange the equation to match whatever answer is given on the exam. So that's going to be question 1. Hopefully it wasn't too bad. Let's move on to question number 2. And what I like about question number 2, a nice, simple, easy question. And I feel like we don't have enough of those lately. So hopefully this one will be good to go. So it says, the following is true about the virtual work principle. So this is kind of a theory question. Definitely expect something like this on the final. Dr. Sammer loves these type of questions, and they're really good because they're actually kind of sneaky. All right. So it gives us 4 statements, and then of course it gives us a 5th statement which says both statement B and statement D are correct. So we're just going to go through each one of these and we're going to say if they're correct or not. So if we look at statement A, it says in static equilibrium, there is one particular virtual displacement field which the work done by the internal stresses is equal to the work done by the external forces. So this one's actually false. This one's not true, and the reason why is it says 1. Now, as we see in the principle of virtual work, it could be any displacement field. It doesn't have to be just one, it could be any. Since this answer limits it to a single particular virtual displacement, we know that this is actually wrong. Now, if we look at part B, it actually says that, where it says in static equilibrium, for any virtual displacement field, the work done by the internal stresses is equal to the work done by the external forces. This is exactly true, so we know that B is actually a correct answer. And what this statement basically says is this: the internal virtual work is equal to the external virtual work. And that's what we try and preach over and over and over again. This is what you guys are going to be using in all scenarios. So again, please never stop. Once you get one of the right answers, never stop, because there could be a second right answer. If we look down at statement C, it says the principle of virtual work and the differential equation of dynamic equilibrium are equivalent. Now, just like A, this one is incorrect. So we're going to put a big X through it. And the reason why, it says dynamic equilibrium. This is not true. We know that internal virtual work, or the principle of virtual work, is based on static equilibrium, not dynamic equilibrium. So we know that this one's incorrect. However, statement D says the principle of virtual work and the differential equation of statics, so we see this time it actually says static equilibrium are equivalent. Well, this is exactly true because the principle of virtual work is actually derived from static equilibrium. So as we can see, this answer is actually going to be E, where both statement B and statement D are correct. So nice, easy question. It really tests your guys' theory about virtual work, but this isn't really a problem. Let's be honest. If you guys are in a final exam type scenario, this is one just little fact check away from your notes since it's open book. Not too bad. So let's move on to the last question. Question number 3. Now, question number 3 is actually a really simple question. But this is the question where I mentioned people always like using shortcuts. Now, question number 3 is very quick, very simple to do if you guys do the shortcuts. However, if you guys don't know the shortcuts and you guys are trying to solve this question, and you guys referred to Dr. Sammer's solution, it could be a little bit complicated because you don't know exactly where he's getting the numbers he's getting or what he's substituting into. So question number 3 says the principle of virtual work is used to find an approximate solution for the displacement function of the shown beam. If the assumed actual and virtual displacement fields, which already satisfy the essential boundary conditions, are y is equal to ax1 squared and y star is equal to a star x1 squared, respectively, and EI is the flexural rigidity of the beam, then the principal virtual work would yield what value for A? So if we look up in both of these equations, they both have an A term. And what we're going to do is we're going to solve for that A term in the actual displacement field. All right, so we have our beam here. I kind of drew it a little bit crooked, or maybe it's just me. I don't know. I'm a little crazy. And we have what we have is our, for flexural beams, I wrote what the internal work and the external virtual work is equal to. So again, I'm just going to go down in our two colors. So the first one over here, we have our internal virtual work. So I'll put this right here. This is our internal virtual work. And then the second one's going to be our external virtual work. So I, VW, and then on the other side, we have EVW. Now again, when you go into an exam type scenario, I just recommend writing down these two equations, and then you guys can use these equations whenever you guys want. It should make everything nice and easy to solve for. So what we're going to do, just like before, is we're going to start off with the internal virtual work, figure out what that's equal to. Then we're going to solve for the external virtual work and figure out what that is equal to. So we're going to start with the internal virtual work. So what I'm going to do is I'm going to go IVW is equal to, so if we look, IVW just has one term. It's that integral term. Now, again, why I like to go between A and B rather than from 0 to L like Dr. Sammer has in the notes is because this is all dependent on a smooth function. Now, if we have, I'll put it in green here, this is 0 and this is L, we can see that between 0 and L, it's actually not a smooth function. Because what happens, and I'll highlight this up here, is this concentrated load rate at the center, this will make our displacement function discontinuous. What happens when it's discontinuous? Well, we actually have to split it apart. So if I'm looking at the internal virtual work, I'm going to have to actually take it twice. Internal virtual work 1 and internal virtual work number 2. So 1, I'll have my A and I'll have my B here. So this is going to be for number 1. So what I'll do is I'll go A1 and B1. And then our second one, I'll have A2. And then we'll go all the way here to B2. Now, this is where things start to get to those shortcuts, like I said, because if you guys already know that they share the same displacement function between A1, B1, and A2, B2, then there's a lot of shortcuts you guys can take, and that's what Dr. Sammer did. However, to me, I can find it a little bit confusing because if you guys are trying to use those shortcuts with the provided formula, it's not going to make too much sense. So if we look at the flexural rigidity for beam formula, we have the integral from A to B. So our first integral, again, we're going to go from A1 to B1 because that's the region where it's smooth. If we go to A1 all the way to B2, it's actually not smooth because we have that concentrated distributed load. So from A1 to B1, that is simply from 0 to L over 2. Now the rest, EI, well, that's not going to change over the region. And then what we have is d squared y over dx1 squared. And then what we have is d squared y star over dx1 squared. And this is all with respect to dx. Now what we can do is we say, all right, well, this is for the first region, but we have to include the virtual work of the second region. So this is the region A2 to B2. So what we actually do is we say, all right, well, we have all this internal virtual work from the first region. Well, we're going to add that to the internal virtual work of the second region. So the second region is from L over 2 all the way to L multiplied by EI multiplied by d squared y with respect to dx1 squared. And then we have d squared y star with respect to dx1 squared. And then this is all with respect to dx1. All right. So if you guys look at the solution from Dr. Sammer, he doesn't have this. He just has one simple integral. The reason why is because the y function in the first integral is actually equal to the y function in the second integral. And the virtual displacement in the first integral is equal to the virtual displacement in the second integral. So in this case, what I'm going to do is I'm going to say, all right, well, we know that y is actually equal to a times x1 squared, and we know that y star is equal to a star times x1 squared. So those are the same in both of the integrals. So because of that, what we can do is we can say, all right, well, the internal work is actually just the integral from 0 all the way to L. Because if we're integrating from 0 to L over 2 and then L over 2 to L, well, it's the same as just going from 0 to L as long as everything inside of that integral is the same. So EI, well, that's going to be the same in both of the integrals. dy squared, well, that's the same in both of the integrals, but we know that dy squared is actually just going to be 2a, and that's pretty easy because all we have to do is take the integral of a x1 squared twice, and then we have this the second derivative of y star, which is going to be 2a star, and this is all with respect to dx1. So again, the key here is that the y in both integrals were the same and y star in both integrals are the same. That was a nice assumption from this question, but I guarantee you, in the real world, if you guys are given a beam that's discontinuous like this, and what I'll do is I'll label the two regions. We have region 1 and we have region 2. The y's in both of those regions will actually be different. So this is why I want to show you guys the theory so you guys can see where it comes from. And then you guys can make simplifications if you know that there are simplifications. However, if y in region 1 was different than y in region 2, and you guys just try and integrate from 0 to L at the beginning, you guys are going to run into a lot of problems. So again, this is why I'm trying to teach you this. It's taking up a lot of time and making the video longer, but again, I hope it helps you guys in the long run. So what we can do is we can actually simplify this a bit more, because what we can see is this is going to be the integral from 0 to L EI multiplied by, I'll put in brackets 4, and then times A, and then times A star dx1. We have no x1s in there, so when we integrate, all we're going to get is 4EI times A star, and then times L. So this right here, this is my internal virtual work. All right, guys, so again, this will be the easier of the two. The only trick here is realizing that this is actually two integrals, and what we had to do is realize, oh, since the y's in both integrals are the same, we can make it one integral. Now, when we get into the external virtual work here, this is where things are actually going to get a little bit complicated. So I'm going to go EVW, and this is going to be equal to two things. The first one is the external virtual work of that first region, and then the second will be the external virtual work of that second region. So as we remember, we have two regions, and we're going to have to consider the external virtual work of both of those regions. And the reason why is because it's discontinuous due to that point load at the center, which I called either B1 or A2. Again, that point load makes the thing discontinuous, therefore we have to consider two regions. So what we're going to do is we're going to go through the 5 terms of the external virtual work for each region, and if they're non-zero, we're going to add them to the equation below. So I'm just going to go through and we're going to look at region number 1 first. That's the region here spanning from A1 all the way to B1. And if we look at the first term of the external virtual work, it's basically the integral of the distributed load. Now, if we look here, we have no distributed load between A1 and B1. Therefore, we know that this is going to be 0. So we don't have to worry about that at all. Good to go. So I'm going to erase the highlighting there, and we're going to move on to the second term. Now, the second term is VB, so the shear at B, times the virtual displacement at B. So if we look here, we know that B1 is actually this point right here in the center of the beam. And we know that right there, well, of course, that'll have a displacement, and that is going to have a shear. So this term will need to be included. So I'm going to come down here and say, all right, for the first region, we know that we have a negative V, and this is at B1. So I'm just going to put B1 to really make it stand out. And then this is times or multiplied by the virtual displacement at B1. All right, so that one comes from the middle of the beam. And let's move on to the next term. So I'm going to erase the highlighting over here, and we're going to move on to that third term, which is VA times the virtual displacement at A. So we know that A is actually at the very left-hand side of the beam right there. And of course, there is going to be a reaction force. So we know that there is going to be some shear at A over there. That's not very hard to not very hard to see. The thing is, though, we also have that second term, the virtual displacement at A. So that virtual displacement at the fixed end. Now we know that since the end is fixed, there is going to be no displacement. So in this case, our virtual displacement at A will be equal to 0. Therefore, the whole term will be equal to 0. We don't need to include it. And again, that's because we're dealing with a fixed end. There is no displacement at a fixed end. All right, so I'll erase this right here. And we're going to move on to the fourth term, and that is mb times the rotation at B, or the virtual rotation at B. So again, this is at the center of the beam, and we know that there is going to be a moment, a bending moment inside of that beam at point B, and we know that there's going to be a rotation there at B as well. So this term will need to be included. So what I'm going to do is I'm going to scroll down here, and we know that we have to go, all right, plus the moment at B1 times the rotation, or that virtual rotation, at B1. So we're going to have to include this because it's fairly easy to tell. At the center of the beam there, we are going to have a bending moment. And I don't mean bending moment in what I mean an applied external bending moment or a concentrated bending moment. I mean, if we look at the moment profile of this beam, there's going to be some moment there. So we have to include it. So that one, again, not very hard to see. Now moving on to the last term, we have MA times the virtual rotation at A. So again, we're looking at that fixed support. Of course, it's fixed. There is going to be a moment there. However, since it's fixed, we know that the rotation at A1 there, that rotation is going to be 0. Therefore, this last term right here, this will be equal to 0. Not very hard to see. So that is all 5 terms for the first region. Again, that region was from A1 to B1, so I'm going to erase these 2 points because now we're going to have to do the exact same thing, except we're going to be looking at region number 2. So this is region number 2. So we're going from what I call A2 all the way to B2. So this region right here, and again, we're just going to go through the 5 terms. Looking at the first one, we see that it's the distributed load. And from A2 all the way to B2, we know that there is no distributed load, so therefore that is going to be 0. All right, so moving on to the next one, we have the shear at B multiplied by that virtual displacement at B. So again, now B is always the one on the right-hand side. So this is our new B over here, which is B2. And we know that there is going to be shear there, and there is going to be some sort of displacement there at B. So what I can do is come down here and say, all right, well, we have a negative, and I'm going to put B2, or not uppercase B. We have the negative shear at B2 multiplied by the virtual displacement at B2. As we're going to see, we're going to swap in B2 for L's and X's later on, but this is just for now. So now we're done with that second term. I can erase it, and I say, all right, well, my next term that I have is plus VA times Y star at A. So now I'm looking at the middle of the beam again, at that point A2, and just like we discussed in region 1, there is going to be shear there, and there is going to be a displacement. So I will have to include this VA multiplied by Y star at A. So I'm going to come down here. I'm going to go plus V at A2 multiplied by that virtual displacement at A2. All right, so that's that third term in the equation. I'm going to come down here now. I'll erase this so you guys can always keep track of where I'm at. We're looking at plus MB times the rotation at B. So if we look here, this is at the end of the beam at that point B2. And we know that at a free end of the beam, or an end where there's no support, the moment there is going to be 0. So therefore, we know that MB in this case is going to be 0. We know that this whole term will actually be 0. So we don't need to worry about this term. Now, if we move on to the next term, though, we have minus MA times, and remember in this case, that that point A, that's A2, which is at the center of the beam. And just like we discussed in region number 1 here, we know that there is a moment at that center of the beam, an internal bending moment. So we need to include this term. So what I'm going to do is I'm going to say, all right, we have a minus M of A1 multiplied by a rotation at A1. So A1 star. And now we can see we've been through all of the terms. We're good to go. So what I'm going to do actually to make our lives a little bit easier is I'm going to erase the highlighting first of all really quick, but I'm going to copy this beam and I'm going to bring it down below because this beam will show us where Dr. Sammer and where everyone gets those shortcuts from. So I'm going to copy this. We're going to scroll down here. And what I'm going to do is I'm going to paste it. And this paste will make things hopefully nice and easy. I'll put it up here. And then we'll go down at the bottom. So this is our equation, and we want to try and simplify it. So I'm going to go equals to, and the first thing that I notice is the location B1 is actually equal to the location 2. They are the exact same location. All right, so because of that, we can actually do some simplification. So what I'm going to do is say, all right, well, I see that there's a couple times I got the term B1, and there's a couple times I have the term A1. For instance, right here, or A2, sorry, not A1, right here and right here. So what I'm going to do is I'm going to say, all right, well, since we know that B1 is actually equal to A2 in terms of location. Now I'm going to keep that in mind in terms of location, and I'm going to explain why that changes a little bit later on. We can say, all right, well, y star of B1 is actually equal to, and I will write this down here, y star at B1 is equal to y star at A2. So because of that, I'm going to group all of those nice terms together. So I'm going to look around and say, all right, well, I got a shear at B1 and a shear at A2. Well, I'm going to group those bad boys together. So what I'm going to do is I'm going to put in brackets here, I'm going to have the shear at A2 minus the shear at B1. And this, of course, is multiplied by y star at B1. Now, y star at B1, that virtual displacement at B1, this is the same as that virtual displacement at x is equal to L over 2. So x1 is equal to L over 2. So there's my first term I'm going to group together. And I actually probably move these up just a little bit so that they don't get in the way at all. Alrighty. All right, so that's my first term. Well, I'm going to say, all right, well, I also have a negative shear at B2 minus y star, so I'm just going to leave that. Negative V at B2 times the y star at B2, and we can say that B2 is actually the location of x1 is equal to L, because again, we know that B2 is at the end of the beam. Good to go. But then we also have another term. We have that moment term. So this is going to be plus, and I'm going to put in brackets. We have the moment at A2, or we got to see which one's negative. We got the moment at B1. Not what I wanted to do at all. Come on, one more. There we go. We have our moment at B1 minus our moment at A1. So I'm going to go moment at, this should be A2, sorry, minus the moment at B1. And then this, of course, is times by the rotation, or the virtual rotation. And again, this will be at x1 is equal to L over 2. So this is our virtual work here. And now this is what we get when we do things the theoretical way, or from those equations that we get. Now, if you look at Dr. Sammer's work, or anybody that does this quickly, they never have the shears and the moments. They use relationships that they know about. So one of the things that we have to realize is kind of the moment profile of this beam. We know that it's going to have some sort of moment profile, and this is going to look really bad cutting through everything. But we know that it's going to probably look something like this. Of course, it's not going to look exactly like this, but it's going to look something like this. And the reason why I'm saying this is because if you look at location B1, which is right here, and we look at location A2, we see that the moment there is actually the exact same. So we know that M A2 is actually equal to M of B1. Therefore, this right here, this whole term, this is equal to 0. Because the difference between those two moments, well, that's actually equal to 0. So there's kind of the first thing that we keep in mind. And this is expected. If you guys look at the shortcut ways, we never have a concentrated moment in there. And this is why, because the moments are the exact same. So let's look at the shear profile. The shear profile is a little bit easier to understand because we know it's going to be something straight right here, and we know it's going to drop, and then it's going to come across straight, something like that, and then it's going to drop yet again. So this is very easy to see because we know that the shear at B2, so at the end of the beam here, and I'll put a circle here, we know the shear at that point, well, that's actually just equal to P. So we know that B2 here, or the shear at B2, this is equal to P. Now, if we look at the first one, if we're considering the shear at A2 minus the shear at B1, well, this is saying the same as I want to take this shear and find the difference between the shear up top here. Well, we know that that difference is actually a magnitude of negative 2p. We start up here at b1 and we go down by a magnitude of negative 2p. So this right here, we know that this is equal to negative 2p. And again, that just comes right from the shear diagram. So this is where the shortcut comes in. And I'm going to be terrible at explaining this, but if you guys realize that the difference between the shears between points is actually just equal to the applied axial load, you guys don't need to use this big long equation. You guys can just say, oh, it's going to be 2p multiplied by the virtual displacement at x1 is equal to L over 2. Nice and easy. But this is the way you guys want to do it. If you guys don't know and all you have is the theoretical equations, this is how you apply them. So what I can do is come down here and say, all right, I can simplify this quite nicely. I have negative 2p times the virtual displacement. So y star at x is equal, or x1 is equal to L over 2, and then minus my p times my virtual displacement, y star, at x1 is equal to L. So x1 is equal to L. So now it's looking pretty nice, but it gets even nicer because I'll put a little note up here. We know that y star is actually equal to a star times x1 squared. This is something that we're given right away. So what we can do is we can substitute this into the equation. So I'm going to come down a little bit and we'll say, all right, well, we have negative 2 times p. That doesn't change. But then we have y star at x1 is equal to L over 2. So all I need to do is substitute L over 2 equal into our y star equation. And what I get is I get a star times L squared divided by 4. Not bad. All right, carrying on, I got a negative p again. Then I got another y star, but this time at x1 is equal to L. All I need to do is sub L into that equation. I get a star times L squared, something like this. And as you guys can see, this can be nicely simplified into negative 3 over 2 times p times a star times L squared. And this right here, ladies and gentlemen, this is going to be our external virtual work. And this is great because it means that we're one step away from finding our final answer. So again, this is our external virtual work. The last thing that we need to do is say, all right, well, we know that our internal virtual work is equal to our external virtual work. Well, therefore, we take our internal virtual work, which we have up above here as 4EI, and I'll just kind of put a little arrow here. This is our internal virtual work. So 4EI, A times A star times L. So I'm going to come down here. We have 4 times EI, A times A star times L. This is going to be equal to our external virtual work, which we have right above there, which is equal to negative 3 over 2 times p times a star times L squared. And what's nice about this is we can see that there is stuff on both sides that cancel out. For instance, I see that I have an a star on both sides. I'll get rid of that. I see that I have an L on both sides, so the L on the left-hand side cancels. The L on the right-hand side goes from L squared to simply just L. And therefore, my only unknown that I want to solve for is going to be that A. So therefore, I can rearrange this and say, all right, we can solve for A. A is going to be equal to negative 3 divided by 2 times 4. Oh, wait, that's just going to be 8. And then at the top here on the right-hand side, we have a P times L. So P times L. And this is going to be divided by what's on the left-hand side, which is going to be an E times I. And this right here is going to be our final answer. So I'm not sure which answer this is on E-class, but this is how you guys get it. Now, I want to apologize. If you guys really, really love those shortcut methods that you guys can find that external virtual work really, really simply, please do it. Don't do it the hard theoretical way. I want to show you guys a theoretical way because if you guys are ever in a pickle, something like that, you guys have the equations, you guys can solve for it by yourself. It's not going to be a problem for you guys. Why I'm doing this, again, it gives you guys that backup option. But the shortcut way, it's nice and easy, and honestly, it's not too hard. I'm pretty sure you guys know the shortcuts for finding that external virtual work. No problem at all. All right, so that concludes this quiz tutorial. I hope you guys enjoyed it. We only really have one more big quiz tutorial left, so it's going to be a sad time when that last recording hits. You guys have been great this semester. It's always so much fun talking to you guys. So again, thank you guys so much for listening. I really appreciate it. I will see you guys in quiz number 30.